Bismillahirrahmanirrahim. This is lecture number 13 of Thermo 2, Axial Flow Reaction Turbines. The reaction turbine applies the principle of both pure impulse and pure reaction turbine. Each stage of the reaction turbine consists of a fixed row of blades over the whole of the circumferential annulus and an equal number of blades on a wheel. So as shown in this diagram on the right, in each stage of a reaction turbine, there is a row of fixed blades connected to the casing, and there is a row of moving blades connecting to the rotor or the wheel. Admission of fluid in the reaction turbine takes place over the complete annulus, and so there is full admission. The fixed blade channels are of nozzle shape, and there is a comparatively small drop in pressure accompanied by an increase in velocity. The fluid then passes over the moving blades, and as in the pure impulse turbine, a force is exerted on the blades by the fluid. There is a further drop in pressure as the fluid passes through the moving blades. Since the moving blade channels are also of nozzle shape, and therefore there is an increase in the fluid velocity relative to the blades. Here is a blade velocity diagram for the reaction turbine stage. We start by drawing the common side, which is CB, the blade velocity. On the right side, we draw the inlet velocity triangle, the larger side representing the absolute velocity CAI, and the smaller side represents the relative velocity CRI. On the left side, we draw the exit velocity triangle, the larger side representing the relative velocity at the exit. CRE. And the smaller side represents the absolute velocity at the exit. This is CAE. And this length is CB up to point from O to A. We can also mark the velocity of whirl components. From O to D is the velocity of whirl component of inlet velocity, CWI, and from O to E is CWE. Combined, this is delta CW. Here we can mark CFI as before. And on the left vertical side, we can mark CFE. So essentially, the velocity diagram of the reaction turbine looks similar to that of the impulse turbine. But there will be some differences that we will learn later. This slide shows the HS diagram and the pressure velocity variation. The first diagram is an HS chart. The vertical axis represents enthalpy and the horizontal axis represents entropy. On an HS chart, constant pressure curves are inclined upwards as shown here for pressure P0, pressure P1 and P2. P0 is the pressure at the inlet of the fixed blades at this point. Here the pressure is P0. After the fixed blades, the pressure is P1. This pressure is P1. And at the exit of the moving blades, the pressure is P2. So this pressure is represented by these three curved lines. The process in a turbine is adiabatic. A reversible adiabatic process is shown by a vertical line on the HS chart representing an isentropic process. Practically, there is some deviation from the isentropic behavior. So we represent an actual adiabatic process by a dashed line curved inclined towards the right side, as shown here from process 0 to 1 to 2. So enthalpy before the inlet is 0. After the fixed blades, enthalpy is H1, and at the exit of moving blades, enthalpy is H2. The diagram on the right shows the pressure and velocity variations. In the fixed blades, which are of nozzle shape, pressure decreases and velocity increases. So this is a typical behavior of a nozzle. Drop in pressure is transferred to increase in the velocity. Then the moving blades, they are also of nozzle shape. So pressure further drops in the moving blades. The absolute velocity decreases. However, the relative velocity of the fluid with respect to blade increases. Degree of reaction. As mentioned earlier, in a reaction turbine, there can be an impulse force as well as a reaction force on the moving blades. So the reaction effect is of 1 degree since the impulse effect is always there. The degree of reaction is defined as the enthalpy drop in the moving blades divided by the enthalpy drop in the stage. This is equal to H1 minus H2 divided by H0 minus H2, where H0, H1 and H2 are the enthalpies of the steam at inlet to the fixed blades, at entry to the moving blades, and at exit from the moving blades respectively. For a simple impulse turbine which has no reaction effect, the degree of reaction will be 0. And for a pure reaction turbine which has no impulse effect, the degree of reaction will be 1. So here this is equal to 1. Degree of reaction will be 1 for pure reaction turbine. For the Parsons type of blading, which has the same section for both the fixed and moving blades, the degree of reaction will be half. This means Parsons turbine is 50% impulse and 50% reaction. Here is a velocity diagram for the Parsons blading, that is 50% impulse and 50% reaction turbine. The fixed and moving blades are geometrically similar. Therefore, the velocity diagram must be symmetrical. So in this diagram, the opposing angles are equal. That is this angle alpha I, which is the inlet angle for absolute velocity, or also nozzle angle. This will be equal to the angle beta E. And this angle, which is alpha E, exit angle of the absolute velocity, this must also be equal to beta I. Then the opposing sides are also equal. The CRE will be equal to CAI. And similarly, yes, this is correct. CRE is equal to CAI and CAE is equal to CRI. And the vertical sides are also equal. The inlet flow component CFI will be equal to the exit flow component CFE. So we call both of them as CF. enthalpy drop and energy input in a Parsons turbine. So we have just discussed that pure a Parsons turbine is 50% impulse and 50% reaction. So the degree of reaction should be equal to half. Therefore, the total enthalpy drop in a stage H0 minus H2 will be equal to 2 times that of the enthalpy drop in one row of moving blades H1 minus H2. Next, we can write a formula for energy input to the moving blade wheel. In a reaction turbine, there are two types of energy inputs to the moving blades. One is the kinetic energy of the fluid entering, which is CAI square divided by 2. And second is the enthalpy drop in the moving blades, which can also be equal to the difference of the relative velocities square, CRE square minus CRI square divided by 2. Since CRE is also equal to CAI, this formula simplifies to the energy at input per unit mass flow rate is equal to CAI square minus CRI square divided by 2, where we can calculate the CRI by this direct formula. CRI square is equal to CAI square plus CB square minus CAI CB cos alpha I. So either we can solve the velocity triangle to determine CRI, or we can use this direct formula, which is given by the cosine law. Next, power and efficiency of Parsons turbine. Rate of doing work per unit mass flow rate is equal to CB into delta CW as before for the impulse turbine. Delta CW in this case can be equated to 2 CAI cos alpha I minus CB. This is a direct formula only applicable for the Parsons turbine. Therefore, the diagram efficiency of 50% reaction turbine is given by eta D is equal to rate of doing work divided by energy input. So you can write intermediate formulas here, like this will be equal to CB into delta CW over CAI square minus CRI square divided by 2. And if values are substituted and the formula is further simplified, this becomes equal to 2 into CB over CAI into 2 cos alpha I minus CB over CAI divided by 1 minus CB over CAI square plus 2 into CB over CAI cos alpha I, where this term, which is repeated in this formula, CB over CAI, is known as the blade speed ratio.